Hello viewers, welcome to video number 70 of channel Chemphilic. Video number 70 is the 12th episode of Chemical Thermodynamics, and the topic of this 12th episode of Chemical Thermodynamics is internal energy. So let's start. Internal energy, that is the energy associated with the system or substance that depends upon the chemical nature and temperature, pressure and volume. Okay. Second point, internal energy is microscopic level of energy. Earlier also I told you this point, and this microscopic level of energy, which is highly disorganized form of energy and has component like intermolecular forces which change continuously. This microscopic level of energy, it has also two components. The kinetic energy in the microscopic level is consisting of translational, rotational and vibrational motion of the atoms and subatomic particles. Whereas potential energy in the microscopic level consisting of the attractive and repulsive forces between the subatomic particles and intermolecular forces, and all these parameters change continuously, so it is highly disorganized form of energy. Therefore absolute value of internal energy cannot be determined, but the change in internal energy accompanied by a process is measurable quantity. So change in internal energy delta E, which is equal to E2 minus E1. E2 is the internal energy in the final state, E1 is the internal energy in the initial state. This change in internal energy when the system goes from one state to another state can be measured. If E1 greater than E2, the extra energy possessed by the system in the initial state is given out, and in that case change in internal energy sign will be negative because energy is given out. If E2 greater than E1, then energy will be absorbed. In that case change in internal energy will be positive. And internal energy is an extensive property, that means the property which depends on the amount of the matter or quantity of the substance. Next point, internal energy is a state function, that means it depends, change in internal energy depends on the initial and final state of the system but not the path followed. Now let's discuss in details. So, from first law of thermodynamics, we know that heat absorbed at constant pressure, here we are considering heat absorbed at constant pressure goes to increase the internal energy of the system, and plus system performs the pressure volume work, that is the work of expansion. So whatever heat is absorbed, it is divided into two parts. One part increases the internal energy of the system and another part is utilized for doing the pressure volume work. And when there is an increase in internal energy, then temperature also will increase. If internal energy decreases, temperature decreases. So internal energy can change the temperature. Therefore, internal energy, what we can write it as internal energy is a function of temperature. Okay. And therefore, this change in internal energy delta E proportional to the change in the temperature. So, if temperature increase is more, or if internal energy increases more, the temperature increase also will be more. So change in internal energy proportional to delta T. Okay. And you know, for isothermal process, this change in temperature, that is delta T is equal to 0. That means temperature remains constant. When temperature remains constant or delta T is equal to 0, then there will be no change in the internal energy, or change in the internal energy is 0, because internal energy is a function of temperature. So change in internal energy also is a function of change in temperature. If delta T is 0, change in internal energy also 0. In that case, that means in isothermal process, whatever heat is absorbed at constant pressure, it is completely utilized to do the pressure volume work by the gas, or the work of expansion. So, what we have observed, that delta E, this is proportional to delta T. And again we know delta E proportional to mass, because internal energy is an extensive property. Okay. Now, combining this both, what we can write it as delta E proportional to delta T and M. This is for solid and liquid. Okay. Solid and liquid. Okay. Gaseous state I will discuss separately. So, we can write it as delta E. If I want to remove the proportionality, some constant delta T into M. This constant S, this is known as the specific heat. What is specific heat? Specific heat is the amount of the heat required, to increase the temperature of 1 gram of a substance by 1 degree centigrade. Okay, that is the specific heat, and this I am telling for solid and liquid. So, specific heat S is equal to, you can write heat required divided by change in temperature, because it is for change in 1 degree centigrade, again divided by this mass, because it is for 1 gram. Okay. So, specific heat is equal to this one. Now, for gaseous substance, once again this internal energy change is proportional to the change in temperature, because internal energy is function of temperature, and internal energy change here, it is proportional to number of moles of the gas molecule. So N gas. So N is the number of moles of gas. Okay. So combining these two, what we can write it as delta E is equal to your N into delta T. Sorry, this is proportional. Okay. If I want to remove the proportionality, then what we can write? Delta E is equal to some constant, this is proportionality, okay, some constant into N into delta T. Okay. This constant CV, it is known as the molar heat capacity at constant volume. What is that? Molar heat capacity at constant volume, this CV, that is the amount of heat required to change the temperature of 1 mole of a gas by 1 degree centigrade. So, this CV, how can I express? CV is equal to heat absorbed at constant pressure divided by change in temperature, and this is for 1 mole. So, once again divided by number of moles. And from first law we have seen that heat absorbed at constant volume is equal to the change in internal energy, or here increase in internal energy. So what we can write? This is equal to delta E divided by delta T into N. So from this what we can write? Delta E is equal to CV into delta T into N, this equation. So this is very, very important equation. Now, coming to the next point, that this internal energy, it is a state function. State function means its change in value depends on the initial and final state of the system, but it does not depend on the path followed. Okay. So we have to prove that. So we prove it, that internal energy is a state function. Okay, you have to prove it. See, just we are plotting the pressure volume curve of the gaseous system. Just imagine the system is in state A, gaseous system. It goes to state B via path 1 and comes back to state A via path 2. So, this is a cyclic process. Cyclic process means system start from initial state, it undergoes the processes and once again come back to the same initial state. So, change in all this macroscopic property will be 0 because it has come to the same initial state. Now, if I consider when the system, that means it's gaseous system, when the gaseous system goes from state A to B via path 1, then increase in internal energy, that is equal to say delta E. And when it comes back from state B to state A and then when comes back from state B to A via path 2, then decrease in internal energy, that is equal to delta E dash. And we are putting another condition, delta E greater than delta E dash. If I put this condition, then what will be the situation? While going from state A to state B via path 1, increase in internal energy is more, but coming back to state A via path 2, decrease in internal energy is less. Increase is more, decrease is less. That means during this cyclic process, some energy is generated. If you repeat this cyclic process again and again, then it will be you will be continuously generating the energy, which is against the first law of thermodynamics. Energy cannot be created nor destroyed. Therefore, delta E must be equal to delta E dashed. Okay. So, change in internal energy via path 1 must be equal to change in internal energy via path 2. So, internal energy change depends on initial and final state, not the path followed. So, it is therefore internal energy is state function. So, hope you have understood. Thank you.